I'm Ham Iqbal, and today Hasib Bajwa and I will be presenting on friction stir processing, a method of enhancing mechanical properties. Introduction and need. Welding is used to join pieces together to form structures. Structures of iron are easy to join by welding, but this traditional welding does not work on other metals, creating cracks. These sheets or pieces can be joined by nuts and bolts, but this adds to the weight of the system. Minimizing the weight of the structure is a priority in the aerospace industry. More weight means more fuel is needed to move the body, costing more dollars to the already expensive program. This additional weight causes stress to increase when the body moves through space. The alloy of magnesium WE43 is the ideal contender for the aerospace industry as its strength-to-weight ratio is higher than its peers. Traditional welding has not been successful on this metal. Friction stir welding. This is where FSW comes to the rescue. This technique uses a rotating tool to generate heat, which softens the metal on both sides to form a weld. Now the pieces are connected without the addition of any extra weight. As the name indicates, it uses friction generated by stirring the tool to form the weld. Different properties, different materials. Just as we cannot heat everything up to 1000 degrees Celsius because aluminum will melt way quicker than steel, so we need to find the amount of heat that we need to generate to achieve a perfect weld. To do that, for the magnesium alloy WE43, we did trial runs with different parameters. We managed to find the best possible parameters in terms of RPM, translation, dwell time, and depth. However, we still experimented further by writing the loads. The figure shows the welds for the stated weld.
As I have mentioned, we performed various test runs while changing the load to achieve a sound weld. The defect-free weld was analyzed and the improvement of the surface hardness was reported when compared to the base metal, as shown in the slide. Before continuing, I would like to show you a trial run of FSP. After nailing the parameters shown here, we performed continuous welds to produce the whole sheet. FSP sheet of W43 is shown here, and the cross-section analysis of the sheet was done, which is shown below to pattern the microstructure. Now the problem of doing multiple beads arose, which includes heat retention. As we are doing multiple welds, the heat remains inside the plate and it's not distributed evenly, which promotes grain growth. As you can see in the chart here, grain growth leads to drop in the mechanical properties, which is undesirable. In order to lock the microstructure that is achieved, we need to cool it quickly, and this fast cooling will lock the microstructure and prevent any grain growth. In order to do that, we developed a copper heat exchanger to absorb this excess heat while the FSP is underway. This locks the microstructure by effective heat dissipation from the sheet to the coolant, which is initially at -20 degrees Celsius. This shows the cooled FSP setup that we have in the lab. You can see the copper tubings entering the copper heat exchanger, which is located under the FSP sheet. Moving on to the cooled FSP and its properties, the setup has been designed already, as I showed you, and the tests are currently being performed. The analysis will be done to evaluate if the coolant is cold enough to absorb this excess heat to lock the microstructure. Our preliminary data suggests that improvement of 2 to 3 hardness test values, and we will continue to do more tests with lower temperatures, and we will include this data in our thesis. Thank you.